Hello, lovely Internetopians. Welcome to another exciting episode. Today we're going in and we're doing some more updates, optimizations. We're working on the ChatGPT created game engine called Jazg because I couldn't come up with anything more creative than JavaScript game engine, Jazg. So we have the sounds you hear in the background are the game we made for the game jam. For some reason, after sitting for some time, oh, we're damaged beyond repair. That's why. Oh, we can fix it once. Haha. Well, there's the game. You notice it's a bit laggy. Part of that is my computer is not very beefy and it does not handle running this engine in the browser plus streaming very well. It struggles. It struggles. So that's part of the issue. We're sitting here around 19 to 30 FPS with some dips down to like the single digits. So it's kind of rough. So I did a profile on it. Did some, what you call it, performance profiling. Yes, I did some profiling on it. And it turns out it's bad. It turns out it's bad. It's kind of bad. But most of that badness comes from collision checking. This cornfield has most of the 300 some entities in it. Probably 300 of the 300 some entities are corn. And corn, well, that's a lot of collision detections it has to do against everything. So our big optimization is going to be to take all those entities and throw them into a XY sorted array so that we can do we can pass a polygon into the array, and then we can do a collision check on the polygon, right? So I can check the whole polygon, or I can say, okay, here's the polygon with its transform, so it's going to go here, and now I'm going to check the corn plants in this area. I'm going to check, right? So I have a upper, a min, and a max, X and Y. So I can just check those points, any corn in those points, to see if it's in the polygon. And I can just do point and polygon checks instead of having to do polygon on polygon checks. So that's a lot of reduced checks that we have to do on collisions with the cornfield. Because the corn is in a grid of sorts, that allows us to basically make it a lot nicer, a lot more, a lot better defined. A lot more efficient. Yes, it makes it a lot more efficient. So that right there is the plan. I don't think this chat actually is for this live stream. I think that's from a previous live stream. I'll just close that. I won't be able to see if you post anything. I'll just pull this up on my phone so I don't have to worry too much about it. All right. The other thing we need to work on is getting particle systems a little more usable. I'm just going to leave it at that right now. Getting particle systems more usable will make everything better. Okay, so I got chat pulled up on my phone now. I can watch myself. If I wanted, I put my earbud in and listen to myself from 10 seconds ago. Just have to find somewhere to prop this thing up, because all the best streamers just prop their phone up to keep an eye on chat. Okay. All right, so let's dive into it. Let's see if ChatGPT is feeling like helping out today or not. Okay, it looks like it's kind of interested in helping out. It let me log in. Earlier, it wouldn't even let me log in, so that's good. It's technically I didn't log in. I just refreshed the existing. And now it starts. Okay, where am I? Where is my brain? Put your brain back in your head. If you don't, then you'll be dead. Did you hear? That's what I said. Put my brain back in my head. Okay. ChatGPT. All right. I'm going to just throw it the collision system, the whole thing. Well, tell me about that. I'm going to say this is really expensive. How can we optimize it? I optimize this. Time. Efficiency. Yeah. Efficiency. There we go. Optimize it for time efficiency. Let's see what it has to say. There are a few ways you can optimize the code for time efficiency. Use spatial partitioning by dividing the game world into smaller regions. You can limit the number of entities that need to be checked for collisions with each other. This can greatly reduce the number of collision checks that need. This is true. Use broad-based collision detection. This is a method of quickly identifying which pairs of entities are likely to be colliding, so that you only need to perform the more expensive narrow phase collision detection on a smaller set of entities. Use more efficient collision detection algorithm. The current algorithm checks all pairs of entities, which is big O of n squared. You can use an algorithm like separating axis theorem, which is more efficient, has time complexity of big O n log n. Consider using a physics engine library like Box 2D, Chipmunk, or Bullet Physics that are optimized and have been battle tested. Optimize the data structure used to store the active collisions, which is currently an array. You could use a hash table, which would allow you to check if an entity is already in the active collisions list in constant time. If the game is running on a web browser, you could use Web Worker to run the collision detection on a separate thread. This will prevent the game from freezing and will reduce the time the browser spends during collision detection. It's also important to keep in mind that the specific optimizations you should use will depend on the specifics of your game, so you will need to experiment to find the best approach in your case. No, I mean, kind of, yes. Kind of. I get annoyed when people give me this answer, or machines. specific optimizations will depend on the optimizations of your on the specifics of your game, yes, but in general, there is a more things are more optimal or not more optimal, just generally across the board. And so I can just make them as generally optimal as I can without having to make them broadly optimal, I guess. Okay, I want to, okay, well, let's optimize as much as we can for the general case. Technically it's big O in squared, but we've optimized somewhat because we're only checking triangle and we're not checking the square. I know it's still big O in squared. I know, but it's strictly speaking, it's not big O in squared. I mean, it's, yeah, it's like, you know what I mean. We're not going through the whole loop, but it's still technically big O in squared. Reuse the collision callbacks. Remove the entities that are no longer in use. Okay, use the performance now function to measure the time taken by each function. Optimize the functions which are taking the most time. Okay. I mean, to start with, we're actually gonna okay. I would like to start by making in my game I have lots of corn. Yeah. I would like to, let's see, it says spatial stable to do some sort of partitioning to reduce the number of adding all the of collision polygon, a or in a function have it in oh, use a data structure like a quad tree or grid. A quad tree is a tree-based structure that recursively subdivides a region into 4 quadrants, each of which you need to check the leaf nodes that intersect with the collision polygon rather than checking all the entities in the game. A grid is similar to a quad tree, but instead of subdividing the region recursively, you divide the region into a fixed number of cells. Each cell represents a region of the game world, and you can store entities within that region in the cell. When checking for collisions, you only need to check the cells that intersect with the collision polygon rather than checking all entities in the game. You can use a quad tree or grid to store the core entities, and keep in mind that spatial partition using a data structure to find the best balance of performance and memory usage. Okay. The best to only point checking for point and polygon collision can be an efficient way to handle collision detection for entities like corn. Typically, simple shapes and have a large number of instances. Instead of using collision polygons for each corn entity, you could use the position of each corn entity as a point and check if yep, exactly. It's inside the convex hull of the collision polygon, or by ray casting algorithm, which involves drawing a ray from the point in question and checking how many times it intersects with the edges of the polygon. You can use a data structure like a quad tree or grid. Okay, which tends to be more what are the of the convex hull versus the ray casting. Simple implement can computationally efficient, especially for convex polygons. It can be used for arbitrary shapes, not just convex polygons. Not accurate for convex polygons or concave polygons. It can be computationally expensive for concave polygons or complex shapes. Ray casting pros, accurate for both convex and concave polygons. It can handle complex shapes with many edges. Cons, more complex to implement than convex hull. Can be computationally expensive for a large number of edges. Generally, if you're working with simple convex shapes and are looking for more efficient solution, convex hull might be the better choice. On the other hand, if you're working with more complex concave shapes and require a more accurate solution, ray casting might be the better choice. It's also important to keep in mind that the performance of these methods will depend on the specifics of your use case, so you should test both methods. Oh yeah, just test them both. I mean, technically I've already had them write the code for me for both, so okay. Let's do And now you rewrite the collision system, the this will be fun. Be best to test an Oh, yeah, of course, yes. Yes, of course. It won't be able to put this whole thing in anyway in one file. I won't be able to get it all out in one go. It ain't that smart. It can't handle it. This button is my new favorite thing. Oh, you can't see it. Hold on. This button. Let me zoom that in for you. Well, you can't see it because you can't zoom in that far. But, hold on. Well, it finished generating. Okay, well. Anyway. See if it's better at continue than it was before. They have done an update since I last extensively tested this. Oh, it looks like it picked up in roughly the right spot. Yeah, it looks like it picked up in the right spot. This example uses a quad tree to store the collision components and optimizes the collision detection process by only checking entities that are in the same quadrant of the tree. It also uses point in polygon collision detection. The update method first clears the quad tree and then inserts all the collision components into the quad tree. It then retrieves all potential colliders for each component and checks for collisions. Using the check collision function, it calls the registered callbacks if a collision is detected. It is important to note that this is just an example, and you may need to make adjustments to the code to suit your specific use case. For example, the size of the quad tree and the method. Please continue discussing. A point and polygon collision check, and how they made this so much better. Oh, or at least this thread is. How the components are stored in the quad tree, etc. So it is important to keep in mind that while spatial partitioning can improve performance, it's not always the best solution. You might need to consider other factors such as the number of entities, the complexity of the entities, and the complexity of the collisions you're dealing with, as well as test your implementation to find the best balance, performance, and memory usage for your specific use case. Okay, let's file, save as. All right, optimized collision looks a lot shorter than collision did. I have a feeling it's missing some code. Yeah, check collision, add your point and polygon collision check algorithm here. For example, return x1 minus x2 times x1 minus x2 plus y1 minus is. I don't understand that. What else have we got here? Oh, kids want, again, All right. No, there, that button does something. What other stub code do we have in here? What else do I need to? Let's zoom that out. There we go. Now we're talking. Put me back in my place over here, out of the way. What other stub code do we have? I don't see any. Clear the quad tree. Okay, well, that's nice. Oh. I need a... Well, yes, you would need an implementation of a quad tree data structure. I'm not sure I really care to use, like, it's a grid, so maybe I should just, with this data type, I should just use a grid. That's the smart way to do it. I don't know why I'm messing with this. I guess it's fun to see what ChatGPT throws at me and how complete it is. Actually, yeah, it's doing all right. Doing all right. It's not giving me bad suggestions. Not what I want. And that's, I mean, there's worse things than that. Okay, it's still going. I'm impressed. Whatever they did seems to work. I mean, so far, maybe it's just this thread, because I've had threads where it does this, and I've had threads where it's just like, derp, I can't. So here it even got the indentation right. This is a basic one. It has a basic method such as insert, query, and clear. You can use the insert method. Please keep in mind that this is just an example, and you may need to make adjustments to the code to suit your specific use case. For example, the size of the quad tree, the capacity of each quad tree, and how the collision components are stored in the quad tree, etc. Yeah. Okay. Now we did all that. Now I don't want to rewrite all my code. I mean, do I actually have to rewrite all my code? Or does this just kind of drop in place replacement? I rename collision. Let's pull them up side by side. Throw this guy in a split vertical. Okay. So we have a collision component. Oh, we're looking at, there we go. It's a lot more. Okay, we have a collision component. Registers callbacks, handles collisions, handles callbacks. Okay. We've gotten rid of the get width and get height functions. And the properties. So that's interesting. With get height. Okay, so now we get into the collision system class. We have a constructor. Get clearer the quad tree. It's not quad tree clearer. Okay, so here we created a quad tree in this new version. Gliders is an array. Gliders is an array. Okay. And then for const glider colliders, we're going to transform them in a collision and insert them into the quad tree. Okay. Let's indent that too far for some reason. It's indenting too far, or our preferred indentation style. Indention, that's my new word. I made it up yesterday. My preferred indentation style. Okay, so we're putting them in a quad tree. The actual components, we're going to access them once and then have what we need for the collision. Okay, so here we're sorting out any active. Well, we're just resetting. So basically, this is this. We were throwing them in an array. Here we're putting them in a quad tree. Okay. Here we're clearing all the active collisions in a collision component. We're not doing that here, so that's something we're missing. But how are we handling processing the collisions, right? So the other way, we're building up a list of all the collisions, and then we're going back through later and processing them all. One reason we do that is to deal with this thing where you handle a collision, it deletes you, and then the next thing that you collided with can't, you're deleted, so it can't do anything with you, or the collision component's deleted. This might not be a problem though. Let I equals collider. So this is just going through all the colliders. Get their components. Counts potential collider equals quad tree, retrieve collision. So now I have one just off the top of my head. As you add things to the quad tree, I could just go ahead and process collisions inside the quad tree, like, because you're already accessing that node. So why not just process the collision, find out if it's a collision or not. If it's not a collision, you further subdivide the tree. If it is a collision, then you don't further subdivide the tree, and you go ahead and process it on both nodes, and then you pass something else in. It says, oh, if it subdivides. If not, you get the idea. Anyway, so we get potential collider. A potential collider is a potential collider equals. Okay, so potential collider is, we're retrieving anything that's in the quad tree at the collision. If potential collider equals collision, continue. Transform 1 equals collider.get component transform. Collision. Let's call out potential colliders. Okay, sorry, I gotta check some callbacks. Here, these collision components don't have a polygon, so when we check collisions, collision 1, collision 2, or we have an XY and a transform. Yeah, it's just checking for point-to-point collisions. You're never going to get a point-to-point collision. Okay, so I'm thinking this doesn't need to be updated every frame, right? I want to reframe this so it's not a system. It's just going to handle the corn. Okay. I want to rewrite this so it's not a, so it never moves, so I would like to this as a this system so that it should some type and then basically just be a self data structure keeps track of corn is and the pass in any and okay. Some component type, and then basically just be a self-updating data structure. Keep track of where corn is. And the collision system can polygons, polygon, transform function. Use it to can pass corneas and checks collide components against. Against the Hmm. There you go. There's chat if I actually want to see it. Okay, does this work? Collision. Check if the collision component's bounding box intersects with the corners. It doesn't listen to me. Maybe I've made things too complicated. Okay, add corn. Remove corn. Update. I'm gonna have to just sit down and write what I want it. Sometimes you gotta do that. Sometimes. I don't want to though. I really don't want to sit down and write another data structure or whatever. Yes, I have to. It's not that big a deal. The tricky part is going to be adding corn, but we can actually make that easier because we don't need a million corn entities now. We can have just a corn struct base. It's not really struct. It's just a class, a corn class that just stores the relevant information. So how old is it? Where is it? And in fact, for where it is, we could actually store it as just a giant array. Yeah, we can just store it as a giant array of the cornfield, right? And then you don't need a transform component because you've got that there. Just for drawing, we'll have to modify, give it a special draw function and have it. They just need a draw function in our render data type component. So then we'll have a cornfield, and you add all your stuff and it grows corn. Yeah, it just grows corn. Things that interact with the corn pass and say, hey, I need to do the thing, and the cornfield is like, dude, cool. So we basically have a cornfield interactor with a callback. Yeah. Kind of like I was building for the particle system but never finished. Okay, let's just do that. Bye, ChatGPT. It was fun. You're just not getting my idea, man. Okay, get rid of this. Sure, we can save it. We'll get back to that. Sorry, my foot's falling asleep. Yeah, you can save it. It's okay. But we're gonna. Yeah, we closed it already. We don't really need the quad tree. A quad tree might come in handy, but we don't need it right now. Okay. In case you're just showing up, what we're doing is we have this game that we built with, well, with the help of my sisters, two of my sisters, for the Ludendar Game Jam, Ludendar 52, on an engine that was programmed basically by long conversations with ChatGPT about what I wanted, and please code it, and please change this, and please change that, and please continue, and you get the idea. Anyway, now we're trying to do some optimizations because if you can see, it's hard to tell, our frame rate's well under 30. I ran a test of ran a profile on it, and it's spending most of its time checking collisions. So that's why we're looking at that corn. You can see there's a ton of corn, and so if I make a special component, collision component for things, or a special tag even for things I want to collide with corn, and I want to make a special system that processes anything with that tag, then and stores where all the corn is, basically a cornfield, then I have simplified everything a lot. So it is possible to have multiple, multiple collision systems and multiple other things. Anyway, you can see this is a little bit laggy now that this has been running for like, I don't know, 20-30 minutes, maybe an hour, I don't even know. And sometimes it just locks up, and that's that. So we just have to go back, reload. Oh yeah, and there's music and stuff. Okay, back to work. So we're gonna make a new file, and we're gonna call this that's not how you name a file. Run upstairs real quick. Be right back. Okay, I'm back. If I can push the right button here, you'll be able to see me. And where are we? We're writing a function, a class. So we're going to need a component for it, right? So we're going to call this a. Okay, first I'm just going to cheat a little bit. I'm going to copy some boilerplate stuff off of here. You know, we're going to copy the whole thing and delete most of it. Okay. So we're going to have a... What kind of components do we need for a cornfield? The system will store all the corn, right? It's going to store it in... I think we're just going to store it in a big array. We're going to try that. If that doesn't work, we'll put it in a quad tree or something. We're going to start by trying to store it in an array. So we're going to rename this, all this. We don't need any of this. Okay, does the corn have callbacks? Even if it does, it's not stored here. That would be stored in the main object. So all this callbacks up with the corn doesn't need to happen. The active collisions with the corn things doesn't need to happen. Vertices, that's all we really care about on this. We're going to call this corn interactor thingamajig. Corn. That's not what we're going to call it. That's what I'm calling it. It's my working title until I decide what to call it. Cornfield. Yeah, there we go. I'm just going to call it cornfield. I-E-L-D. That's how we spell. Okay. I'm going to call it interaction. And we'll just call it cornfield. Okay, so it's going to have vertices. It won't even have vertices. So far, it's only going to have a name. So here's the deal. All it's going to do is check if the corn is in the cornfield, right? Or if the thing is. So we have a collision component on it already, and we have a transform. So we have the polygon stored in the collision, and we have the transform stored in the transform. So what else do we need to store? Maybe a callback function, maybe a callback function, maybe. So let's go ahead and throw a callback in, and we'll push it, pass it to the constructor. callback equals callback. Okay. So we'll say, or well, it'll just be undefined. If it's not there, it'll be undefined. We can check if it's there or not before we call it. We're good in that. Okay, so in its handle collision, does it need a handle collision? No, because all we're doing is if it collides, we're maybe calling the callback. We don't need to know if it has a callback. We don't need to get its width and height. Maybe we do want to be able to get its width and height. No, I think we can just do a min max. Whoops. Okay, see, we simplified that a lot. Okay, so our collision system in our constructor, we're going to have a field equals an array. That is the field width. So we're going to have comma height and the field width. So it's going to be, I'm not sure if I can, I think I can do this. I don't know. Let's ask ChatGPT. It's something it's good, useful for. ChatGPT. There we go. Hey, what is going on? No, go away. Okay. I need to define a 2D array. Can I do, hey, 2D array in JavaScript by creating an array of arrays. 3 by 3. Whoa. Well, okay, alternatively you can use the array.from method to create a 2D array of a specific size. Alright. Hey, monkey. So rows equals 3 from length rows, comma. You can also use array.from method with an arrow function to create it and initialize the array with some values. Okay, we also need to make a corn struct. Okay, looks like I gotta go. I'll be back. See you soon. Bye. I mean, not like leaving. Just a quick break. And we're back. Okay. Doesn't look like I lost anybody there. All right, where are we? We have a million ways we can do it. It looks like you can also use a loop to create an initialize array. Please keep in mind that arrays in JavaScript are immutable, so you can change the size of the array or the values of the elements after it's created. Okay. Yeah. I like this best. Okay. Where did my code go? Field equals with height width. Okay. So we put everything in the array. Well, we made the array. When we make the system, we also want to store the sprite that it's going to be. No, that's going to be stored in a sprite component. We have that as a separate thing that we can just attach to the entity. It's all good. That's just a system. No, it doesn't have entities. But I can store more than one kind of thing in there. Tag them, so I could have like another class, right? Export class. It's just a data structure that we're going to store in there, right? So it's going to be like a cell, and it's going to have some data. So it'll have like constructor. Did I spell that at all right? We're going to have a width or a name. And we're going to have a, it doesn't need a position because that's where it is in the field. Is that going to be the most efficient to loop through an array and grab all the things? Yeah, it's not good. That's not a good way to do it. Okay, the quad tree is going to be better. Because if you have a 300 by 300 circle, that's a lot of checks. I mean, it's just one array, right? It's just one loop through an array. Yeah, if you have like 150 radius, you're checking as a lot of checks. Or if you have a, yeah. So I think we want, you know, I have in my particle system, I have a KD tree. We're now going to put into its own thing. File new KD tree dot. Okay, and we're going to export the class. And that's all we have to do. And then we have to go to particles and we have to import KD. Is that right? Yep. KD tree from KD tree. Okay, and I haven't actually tested this properly, so I don't know if it works or not. Let's find out, right? cornfield. Okay, so we're gonna, we can just copy that from here. Well, I tried it twice. Now, if I got it wrong, I get it wrong twice. Why make one mistake when you can make two? Okay. We got all this code I really don't care about. Okay, so let's, for now, we're just gonna delete all this code. We have it available. I just wanted the structure, the main structure is all I wanted. Okay. So first of all, we need a way to deal with new new things in the cornfield. I really wish this engine worked the other way around and registered components with systems, not with entities. Maybe you could have both structures, the entity structure and the system structure, but it makes it way more efficient to process your entities if they're or your systems if you have a list of all the things, and it makes it then you can overwrite the register entity or register component code with the system. So you can make system.add component and then an entity tag. Yeah. And then you get components from systems. So anyway, it's the other way. If you go around the block the other way to get to the problem, I don't know. It's probably not. It's 6 of one, half to the other probably, but it feels easier for me to deal with what I'm trying to do right now, which is have a way to just. Well, this is gonna have an update, and in its update, it'll add to the. So things it needs to do in its update, it needs to grow corn. So what's grow corn gonna look like? Grow corn has a couple steps. We need to update for corn. Each bit of corn based on DT. So yeah, make the corn grow, pop, or die. Make corn grow, pop, so grow or pop. Okay, so that's the 3 things that corn does. You know, new corn gets sown, new corn grows, new corn pops. Okay, so that's the one thing it's going to do in the update. Then it will go collisions. So get with cornfield components. Okay, we're gonna have a way to add callbacks to the system, right? So I'm gonna say add callback function. Okay, and then we're going to pass to that function, well, ID in a function, or type. There you go. Okay, so this is actually where we're going to store the callbacks, not here. So this cornfield is, we don't need a, yeah. No, that's, just get rid of the polygon. I might want to call back on there because, we'll see. Yeah, that's all. So this callback function should take a self, which is going to refer to the thing that's colliding. So if a thing collides with it, then it needs a way to update itself, right? Of course, we could also we have access to self, we have access to the corn. So we can have one callback that we register here. We don't need a callback here. I think it's better to register it with the system than on an object basis. Like ChatGPT was saying, I should optimize so I'm reusing the callbacks and not having a list on each component. Now, yeah, that's basically what we're doing. We're going to say we're going to register the callback with the system, so we can say cornfield dot register callback, and then when it detects a collision, it can say, okay, here's my callbacks. Okay, so that means in our constructor, we actually need a list, an array of callbacks too. A map, I guess. It'd be nice not to use a map. We'll just put an ID in here. ID. Type. There we go. There we go. Okay, so now it'll have a type registered in its component, in its cornfield interaction component. It'll have a type registered. That will tell the cornfield how it needs to respond when it has an interaction with it. Okay, so basically they're just the functions like damage the corn or whatever. So it's going to take itself and the function will, and so it'll be like, do this to myself and do this to the corn that I collided with. Yeah. Yeah, so you'll register a function that takes two properties, a self and an other. This is what I do to the self. This is what I do to the corn. Actually, it doesn't even need a. It needs a other of sorts. Yeah, it needs a other, but it's not a. Yeah, it's a other, but it's just the corn. So you're just gonna be able to like affect its age, affect its how good it is. It's a what's the word I used? Corn has its age and its yield. All right, that's really all you're going to be able to affect, the age and yield. Okay. So growing corn is going to be pretty easy. So let's go ahead and add corn. Oh, we were going to use the KD tree. Let's figure that out. Yeah. KD tree sorts it by spatially. It sorts it spatially. KD tree, particle system tree. Yeah, we're changing our corn field to a KD tree. You know, it's a corn tree. Yeah, we're doing this, and we're not worrying about that. Okay, and just for reference, let's open our KD tree back up. Yeah, you don't remember. I gotta open it manually. File, open, KD tree, insert. And we're gonna have to modify it a little bit. Generalize it. Query. Just sticking this stuff all down here so I have it for reference. What are my available? Check if the node is a leaf. Okay, so we don't actually use that. We don't use underscore insert. Okay, so let's get some more help from ChatGPT. We'll say, I have this KD implementation, and I would like to add a delete function. Also, I need a way to for would it be to just and then use the to add a delete function to the KD tree, you will need to first search the tree for the node that you want to delete. Once you have found the node, you will need to handle two cases. I just want you to write the code, dude. That's what I don't pay you for. If the node has one or two children, you'll need to find the in-order predecessor or successor of the node, replace it. It's true that it would be best to store everything in an array and use the tree to store index of the array. Then you can iterate over the array. If you're looking for a way to iterate over all the nodes in the KD tree, you can use a depth-first search algorithm such as in-order traversal, pre-order traversal, or post-order traversal to traverse the entire tree and visit all the nodes. Here's an example of how you could add an in-order traversal method. Okay, so you're going to give me the example of the in-order traversal, but you're not going to give me an example of how to use this method by passing the root of the tree and callback function that will be called on each node during the traversal. You can also use the same approach to implement a pre-order and post-order traversal. Okay, I don't think order of traversal's relevant here, so we can just take that and add another. Okay. Well, okay, I got this all. Okay. You can call this method by passing the root of the tree and a callback function that will be called on each node. Okay, actually? Yeah, I did. We'll make dinner soon, buddy. We'll have dinner soon. We. Okay, you use the same approach to implement pre-order, post-order. Okay, I don't really care about the order, so about the delete function. Once you found the no. Yeah, everything's called interactors because, you know, that's what we called them then, because that's what it was written for. Um, I could also use a heap to store them all. There's no real point. No, we don't need a heap. Continue. Heap would not be helpful in this case. Thinking for a second it would, but it's my favorite data structure for some reason. I don't know. Okay, don't judge. Okay. Yes, yes, yes. And here we go. It's coding slow today. We're getting there. We're getting there. It's slow today. Please note that this is just one way to implement the delete function, and it may not work in all cases. The delete function also doesn't check if it's deleting the root node or leaf node. If the tree is very big, the find node method may not be very efficient. You may need to consider other options like keeping track of parent nodes or inserting the nodes in the tree. Okay, I'm not quite sure what is going on about. Oh, no. Get a hole. Hey. What are you? Stop pushing buttons. Some of those buttons do stuff. Okay. Hey, I said stop pushing buttons. Hey, stop. Stop doing things you're not supposed to do and then say sorry. That's not a good way to go about life. Nope. 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 You gotta stop that. No. Alright. It looks like I've got bored kids. I've got to go take care of other things. I'll catch you all later. I'll finish this up another time. It's been fun. Bye for now.